The goal of this chapter is to generate sequences of random values with specific statistical properties. Examples of random sequences that we can generate or encounter in nature are a coin toss, a die roll, the number of raindrops that fall in a barrel during a rainstorm, the instant at which a radioactive isotope such as uranium-235 decays, and possibly the changes of asset prices in the stock market. Truly random sequences, in which the values in the sequence are independent of each other, are difficult to generate in a computer. However, we can design algorithms that generate deterministic sequences that are difficult to predict and therefore look random. If the algorithm is well designed, this pseudo-randomness is sufficient in many practical applications. Let's do a little of computer archaeology and analyze linear congruential generators. This will allow us to understand what types of difficulties one can encounter when designing algorithms to generate random numbers. The linear congruential generator has a number of parameters. For instance, it takes the value k0, which is a seed. This is an integer between 0 and m-1. And then it takes three parameters, a, c, and m. The algorithm proceeds as follows. un is going to be a sample from a uniform 0-1 distribution. This is equal to kn over m. Then kn plus 1 can be obtained from kn by multiplying by the factor a is the multiplier, and then adding c, which is the increment. This will be an integer number, and then we're going to take the remainder of the integer division of that integer with m. This would give you a remainder between 0 and m-1. And we'll repeat these two steps for n equals 0, 1, 2, up to the number of samples that we actually need. Let's see what are reasonable choices for the parameters a, c, and m. This is an example of a particularly poor choice of parameters for the linear congruential generator. So these are the values of m, a, and c. And as we can see from this picture, if we plot the sequence of three consecutive values that this generator actually generates, they are distributed in planes in this three-dimensional space. In fact, in this other picture, we see that there's a relation that links them. This is a second example with a much better choice of parameters, and it's due to Park and Miller, and these are the values for m, a, and c. As you can see from the picture, now these dependencies between three consecutive values of the random numbers are no longer present. In this course, we will use rand to generate random numbers from a uniform 0-1 distribution. This is a built-in function and it works very well, as you can see in this picture.